Welcome to our very first lesson on the concept of magnetism, and we will begin by looking at the concept of magnetic fields, of which I've already begun just a little bit, and we're going to look at the timeline of things, some of the scientists that contributed, of which I will not be able to cover every single scientist, but I'll do my best to mention some of the main players in developing the concept of the magnetic field and really trying to answer the question of, well, why do magnets stick together? It's a very, very, very good question, and people have been trying to kind of answer that question for a very long time, much further back than the 1800s. But that's where we will begin. And our first kind of idea is that a magnetic field exists. It's a 3D region surrounding a magnet, which is an object that kind of can affect certain metallic objects. And it's a field, which means it's going to do the same type of things that other fields we've studied in physics have done, such as the gravitational field and the electric field. The magnetic field also exhibits a push or pull without actually physically touching the object. And that's kind of the idea of where fields come from. And so the next type of field to talk about after gravitational and electric is the magnetic field. So the magnetic field is a 3D region surrounding a magnet, and it can affect certain metallic objects. A few other things to note is that magnetic fields emanate from a North Pole. By the way, our first statement is contributed from Michael Faraday, a scientist from the 1800s that kind of came up with this idea. He studied magnets and magnetism, and he came up with this 3D region. Also, we can say that a magnetic field emanates from a North Pole and points towards a southern pole. Points towards a southern pole or a south pole. So one of the last pieces being how close the lines are to each other, is going to represent magnitude. The magnitude, how strong the magnetic field is. So, for example, a very simple magnetic field is one that a bar magnet creates. And so you have a North Pole, then you have a South Pole. Always two there are, no more, no less. Our magnetic field emanates from the North Pole and terminates at the Southern Pole. And so often we'll see this noted with an arrow such like this. And this happens everywhere in space, in a three-dimensional space. Now that's very difficult to draw, somewhat confusing, and so we kind of just do a 2D representation. And this will kind of continue. Our magnetic field quite frankly, forms loops and emanate from the North Pole and terminate at the South Pole. Now remember, a field tells you how a particular object would interact when coming into this region. And so we can say, okay, let's say I place a metal object that can be affected by a magnetic field here. Well, it's going to want to go towards the South Pole. If I place a metal object here, it's going to be pushed away from the North Pole. If I put a metal object here, it should be pulled towards the South Pole. So that kind of covers the main ideas of magnetic fields, and this specifically for a bar magnet. One of the other things we want to note is that our magnetic field is symbolized by B. B is the symbol for the magnetic field and is measured in T, or Tesla. That's after the scientist Nikola Tesla. And for a few different references, the magnetic field, the magnitude of the magnetic field of a bar magnet, is roughly 10 to the negative 2 Tesla. We can also look at Earth. We'll draw Earth now. So here's our planet. Earth has a magnetic field. So here's the Earth. Here is our magnetic field. From the poles. So here's Earth, here's our magnetic field. Keep drawing these lines. So that's our magnetic field. And our magnetic field looks a little bit like this. We have what we call our North Pole, our South Pole. However, the magnetic field lines act a little differently. They do this. Which might seem okay, but remember, magnetic field always points towards the South Pole. So our magnetic field is pointing towards the South Pole. So actually, the thing we call the North Pole is actually our magnetic south, and the thing we call the South Pole is magnetic north. So that has to do with our own Earth's magnetic field, of which a bar magnet is times 10 to the negative 2. The magnetic field of the Earth is 5 times 10 to the negative 5 Tesla. For reference, an MRI machine is roughly 15 Tesla. And one of the most magnetic objects in our universe, which is called a magnetar. Sounds like a Pokemon. But it's roughly 10 to the 11 Tesla. A magnetar is a special circumstance of a neutron star. And so I'll pull up what an artist's rendition of a magnetar looks like. So a neutron star occurs when a star collapses, and a magnetar is a highly magnetized version of a neutron star. So that's one of the most magnetic objects in the universe, if not the most. And that's kind of what the artists would say it looks like. So that being said, come back over here, and we have some more people to talk about. So start to do this over here. And the next person is a man by the name of Worsted. And he is Danish. He's a Danish scientist. In the 1800s, 1820, Worsted noticed something a little bit different. He noticed that when he passed an electrical current, through a wire to show that it kind of heated up. Electrical currents through a wire can influence, or did influence in his demonstrations, a compass, or the needle of a compass, which is magnetic. So there seemed to be this link between an electrical current and a magnetic component of a compass. And so Oersted started to do some experiments. And these experiments began to link electricity and magnetism. What was discovered, and this is where we start to get into the three-dimensionality of things. So Oersted did two main circuits. He ran an electric current this way. So negative is here, positive is here, and the current should run like so. Here's our current. Electrons flow from negative to positive, and it turned out that a magnetic field was generated from this, and it went in a particular circular fashion. The dotted line represents the three-dimensionality of this. So here is our magnetic field being generated. And so it's not below the wire, it's more kind of in front and behind, if that makes sense. We have a few ways to visualize this much better. And so the main idea was that this straight current generated a circular magnetic field. The other type of experiment, perhaps you may be able to guess where this is going, But instead of letting the current run straight, he twisted it into a coil. So to represent this, we'll kind of think of it almost like a spring. So instead of the current going straight, it has to go through loops. The electricity has to pass in a circular fashion. And what this created was a magnetic field not just similar, but almost identical to the magnetic field produced by a bar magnet. And so when we have a circular current or a rotating current, what we'll end up seeing is that we can produce what may be thought of as a magnetic field through this coil that is directed in a straight line. And so sometimes we say a straight current represents or can generate a circular magnetic field, and a circular current, one that loops, can be used to produce a magnetic field that points straight through the coil itself. So we say a straight magnetic field. And this second one here is actually, this is the application of an electric or an electromagnet. We can actually take something like a bar magnet and wrap around it a coil of wire and then pass current through that coil of wire, and it will amplify the effects of the bar magnet itself. Something to keep in mind of electromagnets is the intensity at which you can amplify this magnetic field. If you want to increase, if you want to have a higher magnetic field, a higher B value, there are some ways to do that, such as increasing the current. If you raise the current, you raise the magnetic field. Or if you increase the number of loops, the number of coils, or if you increase the size of the loops, make the loops bigger. These are all ways to amplify the magnetic field produced by the current, and this will be this actually has pretty profound applications. But we want to talk now about our first introduction to the left-hand rule and the right-hand rule. And these become pretty significant in physics. So left-hand rule, right-hand rule. And so what we want to first say is that for our first thing, the left hand is negatively charged objects, and the right hand is positively charged objects. It's the first big distinction. So when we're dealing with a negatively charged object, or negative charge in general, we're going to be using our left hand. And if we're dealing with positive charge, we use our right hand. So, for example, we can take this, and hopefully it's a little more clear about how this magnetic field looks, and we'll draw it again to end, and hopefully you'll get a better picture. This is current, okay, so it's electrons flowing, so it's negatively charged. So we're going to be using our left hand to implement the left hand rule here, and I always will use a whiteboard marker, but you can easily use a pen or a pencil. And so we have current or electricity that is flowing upwards. So I'll put my whiteboard marker in the same direction as the current. And so what I actually do is I wrap my hand around that whiteboard marker, and my thumb usually points in the direction of the current. So now what we should be able to see is that the way my fingers wrap around the pen or the pencil or the whiteboard marker in this case is the direction that the magnetic field will go in. So my thumb represents the direction of the electricity, and the fingers wrapping around this way and then coming back around here represent that. So if I tilt it a little bit, hopefully you'll be able to see that the magnetic field should wrap around like so and then come back in the direction my fingers point. So in this example, magnetic field points a little bit like this, to be a little more clear. So try to draw that 3D, and hopefully that will make a little more sense. But let's say that this is the wire. Electricity flows that way. This moving electric charge will generate a magnetic field that wraps around the wire like so, and then comes back this way. So that's kind of where the directionality came here, because the other option would be to basically reverse the direction of all the arrows. So this would be kind of the idea here. So it's difficult to draw and visualize, but we'll try. So it wraps wire like so. Now that's for negative charge. Imagine for a moment that we have positive charge, positively charged objects that are flowing in the same direction. Well, for a positive charge, we use our right hand. And the key difference being, okay, it points the exact same direction, but now my fingers actually wrap the opposite way. So on the right side of the wire, my fingers point up. But on the right side of the wire here, my fingers point down, and vice versa for the left side. So positively charged object will create a magnetic field that looks like so. And actually the orientation of the magnetic field is directly opposite when the charge is opposite. So hoping that makes a little bit of sense. It's the first time we'll use this. We'll use it often as we move through magnetic fields and forces, and I hope that makes sense. That's all for now, and talk soon.